Okay, so now that we've seen a little bit about how you would take um, binding data, right, or go from the idea of having a binding interaction, developing a binding model, turning that into an equation that we can then use to fit binding data to and some of the plots that are involved. What happens if the binding model is a little more complicated, right? The derivation we went through was really simple, right? It's just protein with a single binding site, a single ligand, complex formation, simple equilibria, right? What happens if it gets a little more complicated? What happens specifically if I've got a molecule that has more than one binding site, that can bind multiple different things? Then what do I do? Okay, well, there are a couple of cases of this. You think about, let's just think about a situation where we have a protein that has two binding sites, right? This can get quite a bit more complex, but let's take the next case up. What if our protein P has two binding sites? And let's just keep it simple to begin with, and like for the same ligand, right? Not multiple different ligands. Let's just say the same ligand, two different binding sites, but same ligand. All right, well, there are two cases here. We're gonna do the simple one today, and the next time we're gonna dig in to the more bit more complicated one. And so our two cases are, we're gonna have two dissociation constants, right? So let's say we have case one where K1 equals K2, all right? And case two is when K1 does not equal K2. So the simple case that we're going to deal with today is when the two different binding sites have exactly the same dissociation constant. The more complicated case is what happens when they don't have the same binding constant. We're going to deal with this one today. We're going to leave second case for the next lecture. All right. So we know we have one macromolecule, one protein that has two binding sites. They have the same KD. So we can write down something simple. We can write down the degree of binding expressions for each of those binding sites, which would look something like this. Binding to site one would just be equal to concentration of A divided by K1 plus concentration of A, right? And degree of binding for two would just be equal to concentration of A over K2 plus the concentration of A, right? That's pretty easy. But we can also say, well, what's the total degree of binding? How much total millimoles of A are bound relative to the total amount of the protein? Well, that's pretty easy because the definition is exactly the same. The degree of binding total, again, is still just total A bound divided by total P, right? Which means that that's just the degree of binding to the first site plus the degree of binding to the second site. And because we're saying K1 equals K2, right? If we sum those two up, right, it's just equal to A. And we're just going to say K1 equals K2, which is going to equal, like, I don't know, K, right? We'll just do the KD now because it's the same value. K plus concentration of A plus A over KD plus concentration of A. Well, that's pretty easy because that just means the total is just equal to 2 times concentration of A over KD plus concentration of A. Huh, that's kind of cool. And what that suggests is that in general, right, if we do the same thing with 3 sites, 4 sites, 10 sites, if they're all independent of each other, right, even if they're all in the same molecule, but they're all independent of each other, they have exactly the same dissociation constant, the general solution here is that the degree of binding is simply equal to N, the number of sites or the stoichiometry of binding, times concentration of A over the KD plus concentration of A, right? And you'll notice, if you go back and you look at that derivation we did before for the simple single site binding, we got exactly the same form. Concentration of A over KD plus concentration of A. We're in here, right? N equals 1, right? Okay. Now, the cool thing is also, if you took a protein like this that had, say, 2 binding sites, and you do that standard titration, the standard plot, right? You plotted this baby out. Here. Concentration of A, degree of binding, here's 0. Now, our full saturation, instead of going to 1, is going to go to 2, right? And our half saturation point here is going to be 1, right? And our plot is now going to look like this. Right? But the cool thing is now, if you look at the half saturation point here, that's still the KD, right? If you want to satisfy yourself with that, all you have to do is do the same thing I did before. If the point of half saturation, which in this case is 1, but degree of binding of 1, because again, we got 2 sites, that equals 2 times the concentration of A divided by KD plus the concentration of A. What's the concentration of A need to be in order for that expression to equal 1, right? Pretty cool, right? Okay. So with that as a sort of beginning point in our discussions of simple binding, we're going to now, the next set of lectures, elaborate this a bit and start considering cases where the binding is not just sort of to a single site or to multiple sites with exactly the same KD. We're going to start folding in the idea that I started this lecture off with: what happens when those binding constants are different, and more importantly, when they interact with each other.